Bismillah ar-Rahman ar-Rahim. Today we'll be looking at the paper by Cooper. Bismillah ar-Rahman ar-Rahim. Rabbana atina fi dunya hasana fil akhirati hasana wa qina adhaban nar. Today we'll be looking at the Wisconsin card sorting test again and understanding the errors and a slightly different model that exists out there. This is a paper by Richard Cooper. This is published in 2024, if I'm not mistaken. And the idea here is to outline various issues within the WCST test, looking at cognitive flexibility, errors, feedback, and the mathematics essentially behind this type of experiment. So, abstract: the Wisconsin card sorting The Wisconsin card sorting test is commonly used to assess executive dysfunction, particularly in neuropsychological patients. Performance on the test typically yields two types of error. Number one is perseverative errors, where participants persist in applying an inferred rule despite negative feedback. So, doing the same thing again, as in a line of operations, and the feedback is negative. So, it's some type of error, a form of failure that's occurring. And what's happened is that a participant is keep doing the same thing. So that's called a perseverative error. And the second is set loss errors, where participants cease applying an inferred rule despite positive feedback. So that's when someone stops using a line of operations, a logic that is giving a positive feedback, a type of success, a conclusion which they are expecting. So these are cognitive errors that do occur all the time. In this paper, we apply an existing model of WCST, the model of Bishara, to a novel dataset focusing specifically on the distribution of the two types of error over the duration of the task using maximum likelihood estimation MLE. To fit the model to the data, we argue that the model provides a good account of the performance of some participants, but a poor account of individual differences. It is argued that this is because the model is essentially a competence model which fails to incorporate performance factors, and that accounting for the different types of error, and in particular the error distribution during the task, requires incorporating performance factors into the model. Now, some consequences of this for the broader enterprise of developing normative competence models are discussed. Okay, nice introduction there. Rick is actually really great when it comes to really summarizing complicated things into very loose, easy language. Action is prone to error. This is particularly true of sequential action, i.e., action that compromises multiple steps which take place over time. Errors in sequential action take a variety of forms. In some cases, steps within an action sequence may be repeated after the immediate goal has been achieved. Perseverative errors. Okay, in other cases, the immediate goal may be lost or neglected, such that the individual steps become disconnected from the goal, set loss errors. So, as mentioned before, there's a line of operations where you are performing and you get a negative feedback, yet you're doing the same line of operations again. That's a perseverative error. And on the other hand, you have a line of operations that is giving you positive feedback. However, you choose to abandon that line of operations. That is essentially what set loss errors is. Okay, so it's an interesting sort of dilemma many individuals face when they are cognitive inflexible, or I think a better phrase would be when they're cognitively rigid, right? So yeah, both of these type of error may occur when participants perform the WCST. This test is commonly used within clinical neuropsychology to assess executive or more specifically executive function. The classical pattern of performance, indicative of an executive impairment and a feature of many patients with neural damage to the frontal cortex, is the production of high rates of preservative errors on the task, errors that reflect continued use of a response principle despite feedback to the contrary. So, this is a bit more insight into the clinical neuropsychological aspects of this particular experiment. So, that is, of course, very relevant. And in the previous stream from yesterday, I spoke of a great text by Joaquin Fuster, who I don't entirely agree with, but his book titled Prefrontal Cortex, his definition, in my view, is the easiest and most simplistic one to understand. So, this task is also sometimes used to assess efficacy of executive function in neurologically healthy individuals. For example, Miyake found in a sample of 134 college students a statistically significant correlation between the rate of preservative errors on the WCST and performance measures on several simpler tasks that were held to assess the executive function of mental shifting. In the WCST, participants are presented with a series of cards, each showing one, two, three, or four identical shapes: triangles, stars, crosses, or circles, all colored either red, yellow, or blue. There are four target cards visible throughout the task, showing one red triangle, two green stars, three yellow crosses, and four blue circles. Participants are asked to match each card from the series as it is presented to one of these four targets. They are given binary feedback. After each card is matched, the task is to use this feedback to infer the sorting rule being used by the experimenter, which is to match according to color, number, or form of the symbols in the card. Once a participant has demonstrated successful acquisition of the rule through a run of consecutive correct matches, the experimenter changes the rule without warning. The participant must infer the new rule. While there are several variations in how the task has been administered, typically participants are asked to sort either 64 or 128 cards. Right? So it's more than a deck of cards. And typically a run of either 6 or 10 consecutive correct matches is required to trigger the experimenter to change the sorting rule. The WST yields several dependent measures, but the measures that are most widely discussed concern preservative errors, i.e., responses that involve applying the previous correct rule despite negative feedback. These errors have been argued to arise from either failure to integrate negative feedback or inertia in switching away from a previously reinforced rule and in instating a new rule. So, inertia means what? Inertia means inactivity. Okay, so yes, you can at sometimes cognitively be experiencing inertia, but that's not inactivity, that's you just being very distracted. Okay, either way, they reflect a failure of reactive control. A second type of erroneous response that can occur in the WCST is a set loss error. These errors occur when a participant appears to have correctly inferred a rule in use by the experimenter, example given sort according to color, as demonstrated by a run of correct responses, but then produces an erroneous response, i.e., a response not consistent with the experimenter's rule. Despite having only received positive reinforcing feedback over the last series of trials, set loss errors are generally far less frequent than preservative errors. Because I guess, in my opinion, this is just what I think, it's a situation where we are more prone to keeping hold of negative feedback than positive feedback generally. So that's what I think this set shifting situation is amongst both of these errors, that we are more prone to the negative feedback than the positive one. I think so. Phenomenon, phenom, phenomenologically, phenomenologically, they appear to result from interference from alternative possible sorting or attentional drift. Two forms of error are of general interest because they occur across a range of lab tasks. Example: verbal fluency, Resch, Dellis, and Paulus, 2011, as well as in everyday behavior, Reason, 1979. They also dissociate. Sorry, they also dissociate. For example, in studies of WCST performance with healthy aging individuals, the rate of loss of errors. For example, in studies of WCST performance with healthy aging individuals, the rate of set loss errors, but not the rate of preservative errors, correlates with age. Okay, so there's an age factor at play here as well. Interesting. I think this should be highlighted. This suggests that two forms of error arise from different cognitive limitations or limitations to different cognitive processes involved in the task. Given the widespread use of WCST as a clinical instrument, it has been the focus many modeling efforts. It has been the focus of many modeling efforts, including early work by Dehaene and Zhenghu, as well as more recent work by Barcelo. Of particular interest for the current work is the model of Bishara, which provides a formal parametrized, so now it's limited, mathematical account of performance of the WCST, and which yields on a trial by trial basis a probability distribution over response options. Unlike other models of the task, this allows the Bishara model, to be fitted on trial by trial participants' responses using MLE, an approach to model fitting that is generally considered to be superior to fitting the means of group level dependent measures. Ma Young, 2003. In this paper, we report novel, though unremarkable, data from WCSTA and attempt to fit the Bishara model to the data using MLE. In doing so, we propose a slight adjustment to the model. Okay, while the model fit is generally good, to account for participant response that fail to match any rule. So there has to be a situation where if participants fail any of those rules, how do you account for it? While the model fit is generally good, closer examination of errors throughout the task reveal that the model underestimates preservative errors on early trials while also overestimating set loss errors on those trials. It also fits the response sequence of participants who produce few errors on the task better than those who produce many errors. We conclude that while the model provides an adequate account of WCST competence, it is limited as a model of WCST performance. Right, so though it can be a competent model, performance-wise, it's not the best. It seems so. Right, so what's the model of Bishara in this case? Keep in mind this WCST test was created in 1948, went through a couple of changes, so now this model is of focus. Bishara's model performance on the WCST by assuming that participants maintain a set of attentional weights that vary over time. Okay, interesting. How do you weigh attention? Well, how it's done essentially is the response one gives to particular dimensions. And I've also looked at work by Koslin, which I guess I can share here. That when you are looking at the location of an object, contours of shapes, distorted shapes, and visual images, contorted objects, different portions, different locations, so on and so forth, you come to see that there's certain attentional weightage with each phenomena. So, as mentioned here, one per dimension, number, color, and form, and the participants number one use these weights for choosing where to place each stimulus card. Okay. B and B update their weights following feedback after placing each card. Okay, interesting. The basic idea is that feedback allows attention to be focused on a relevant dimension, with positive feedback strengthening the weight of matching dimensions at the expense of mismatching dimensions, and negative feedback weakening the weight of matching dimensions, thereby strengthening the weight of mismatching dimensions. The basic idea is that feedback allows attention to be focused on relevant dimension, with positive feedback strengthening the weight of matching dimension at the expense of mismatching dimension. And negative feedback is weakening the weight of matching dimensions, thereby strengthening the weight of mismatching. Okay, so it's the case of matching in each scenario. Okay, for each trial, i.e., the each card to be sorted, the model uses the dimensional attention weights to produce a probability distribution over the four possible responses. This contrasts with many process models that generate sequences of discrete responses, such that of Dehaney and Shengu 1991, and makes the model ideal for fitting to individual participant to WCST performance measures on several simpler tasks that were held to assess the executive function of mental shifting. This contrasts for each trial the model uses dimensional. Okay, that's perfectly fine. This contrasts with process models that generate sequences of discrete response and makes the model ideal for fitting to individual participant WCST and performance measures on several simple tasks that were held to assess the executive function and mental state. Okay, so this contrasts with this one and makes the model ideal fitting to individual participants. Several simple tasks that were held to assess the executive function. Executive function, okay. Okay, right. Makes sense. In the WCST, participants are presented with a series of cards, each showing one, two, three, or four identical shapes. Triangles, stars, crosses, or circles are colored either red, green, or blue. There are four target cards visible throughout the task, showing one red triangle, two green stars, three yellow crosses, and four blue circles. Participants are asked to match each card from the series as it is presented to one of these four target cards. They are given binary feedback, correct, incorrect, after each card is matched. Their task is to use this feedback to infer the sorting rule being used by the experimenter, which is to match according to color, number, or form of the symbol on the card. Once a participant has demonstrated successful acquisition of the rule through a run of consecutive correct matches, the experimenter changes the rule without warning. Okay, so this is a bit of how, sorry, this is exactly how it works in life. You're used to one particular way of living, way of thinking, then all of a sudden your certain things, certain events compel you to then think different of what's going on, right? And that is essentially the cognitive shift that occurs in one's life. The participant must then infer the new rule while there are several variations in how the task has been administered. Typically, participants are asked to sort either 64 or 128 cards and typically run for either 6 or 10 consecutive correct matches is required to trigger the experimenter to change the rule. Okay, after 6 or 10 consecutive correct matches, the rule changes, which I'm quite intrigued as to why it's a even set of consecutive correct changes, because it says 6 or 10, not 6 to 10, or between 6 and 10, it's 6 or 10. Anyway, the WCST yields several dependent measures, but the measures that are most widely discussed concern preservative errors, i.e., responses that involve applying the previous correct rule despite negative feedback. These errors have been argued to arise from either failure to integrate negative feedback or inactivity inertia in switching away from a previously reinforced rule and in instating a new rule. Either way, they reflect a failure of reactive control. A second type of erroneous response that occur in WCST is the set loss error. I think this is the fourth time mentioned here now. These errors occur when a participant appears to have correctly inferred the rule in use by the experimenter. Example given: sort according to color, as demonstrated by a run of correct responses, but then produces an erroneous response, i.e., a response not consistent with the experimenter's rule, despite having only received positive reinforcing feedback over the last series of trials. Set loss errors are generally far less frequent than preservative errors. Phenomenologically, they appear to result from, excuse me, phenomenologically, they appear to result from interference from alternative possible sorting rule or attentional drift. The two forms of error are general interest because they occur across a range of lab tasks. Right, I think I reread this by accident. Okay. And makes the rule fitting for the participant. Okay, so let's now go on to the mathematics here. Dimensional attention and model initialization. For notational convenience, we follow Bishara and represent dimensional attention as AT as a 3 by 1 matrix. Okay, so I need to take a note of this so I can follow the mathematical logic and sequence here. All right, so we have here AT is tensional dimension. Sorry, dimensional tension. Okay, so that's one dimension we're looking at here as a 3 by 1 matrix. So it's a 3 by 1 matrix. Okay, no problem. Without loss of generality, Bishara assumed that the attentional weights, i.e., the three components of AT, sum to 1.0. Moreover, they demonstrate that allowing the initial weights to vary across dimensions does not significantly improve the model's fit to participant data. Okay, that's a key point. So variance in the initial weights, what's being measured is does not significantly improve the model's fit to participant data. Thus, they assume that at trial t equals to 0, the attentional weights are initially equal. So A is 0.33, 0.33, and 0.33. Okay. Action selection. Now it's a selection of a target pile. So from the cards, it's time for the act of selection. Given the attentional weights on presentation of a card on trial T, the probability of placing the card under the target K. So placing the card under target card K. So presentation of a card on trial T. So presentation TK is the target card. The target card and trial, and then you have presentation. Right, so this is given by transpose. What is transpose in this context? Where M apostrophe T is the transpose of MT. Okay, the match matrix is Q as described below. D is decision consistency. How strongly attentional differences should influence behavior. Okay, so this is represented by PTK. Right, P T presentation of trial. Okay, at target card. This is not right. Presentation of trial target card is equivalent to the transpose of match matrix at target card, and target card is A, D, and T divisible by summation of 4. J is a quantity which must equal 1. Again, you have the match matrix here, comma, another quantity A, and then you have D, and then T. Right, so M apostrophe T is transpose of MT. Then you have the match matrix is what MT is. Okay. As described below, and D is decision consistency. Okay. This is quite key actually moving forward. This particular consistency value, how it switches and changes, is extremely valuable. Okay. A parameter that determines how strongly, because Bishara is using parameters, so this is one of the parameters, how strongly attentional differences should influence behavior. Right, okay. The match matrix at time t, mt, is 3 by 4. So match matrix at time t, mt is 3 by 4 matrix, which in the formulation of Bishara is defined as the following. 1. If the presented card matches target K on dimension I, and 0 if otherwise. So MTKI, MTK I is the identity of dimension. Okay. MTKI is 1 if presented card matches target K, K, dimension, dimension I. So K and I and 0 is otherwise. Okay, right. So this is interesting. Let's see what comes about it once it's calculated. Where the K ranges over the 4 target cards slash columns. And why is it 4? Because you have those 4 triangle, cross, circle, square. I believe that's the other ones. Let me check. So red, green, yellow, blue. Okay. 304. Okay. So adjusting attention on the basis of feedback. Following feedback attention. Following feedback. K ranges. Scope. So it's approximate to fit this. Okay. Adjusting attention on the basis of feedback. Following feedback, attentional weights are adjusted according to equation number 4. Right, so equation number 4 is matched matrix, target card, attention dimension. Sorry. Matching matrix, target card, dimension. A is the quantity, F, T, and I. Okay, I'm pretty sure they're going to explain what this is. Following feedback, attentional weights are adjusted according to equation 4, which defines feedback signal ST based on reward or punishment. Interesting. You have a bit of a Skinnerian Pavlovian situation going on here. Okay, and equation 5, which defines new value of attention matrix. Okay, interesting. So we have here feedback signal of dimension. So ST comma I is the equivalent of matched matrix, okay, target card, dimension again here, okay, and then you have A, and then you have F at the top, and then you have T again, and then you have the dimension again, which is by the summation of 3, what was it again? 3 attentional dimensions, okay. H, this quantity has to be 1, and this is of, i.e. multiplied by the matching matrix of the target card of the quantity H of the value A of F and T comma H if rewarded. So this is reward, and punishment is 1 negative, so it's what the opposite is. So if you remember here, it's 1 if matches, 0 otherwise. So if it doesn't match, i.e. punishment, right, this is what happens. So you have 1 minus the above divided by summation of 3 dimensions h is 1. That is then multiplied by 1 taken away. The reward is now taken away from the equation. Okay, if punished. If punished. Okay. Now AT. AT is what again? AT is here. Positive 1 equals to 1 minus reward times AT plus R times S, and the punishment is the same, AT plus P point S. So feedback signal ST is defined in equation 4, reinforces dimensions that match positive feedback, but punishment dimensions that match following negative feedback. As equation 2, this one here, equation number 2, which we discussed here, this one here, equation 2, states here that as equation 2, the attentional weights are raised to a power f, the attentional focus. Okay, so f is raised to the focus. F is the focus. So okay, A, F, T. F is attentional focus. Interesting. In calculating the strength of a feedback. Okay. Highlight this. This is key. Equation 5 calculates the new attentional weights as a weighted average of the existing value and the feedback signal with parameters R and P, allowing for differential treatment of positive feedback rewards. Okay, that makes some sense as to why they would allow parameters to be in this equation. Okay, all right. I'm going to conclude this with parameters and the plausible ranges. Okay, so just quickly check something here. All right, okay. Okay, so the model includes 4 parameters: reward sensitivity, punishment sensitivity, control how the feedback signal affects the attentional weights. Equation number 5. Okay, these parameters both range from 0 to 1. When 0, the feedback signal is completely ignored and attentional weights persist. When 1, the attentional weights on the previous trial are ignored and behavior on each trial is purely a function of feedback following the model's previous response. Attentional focus, attentional focus F, and decision consistency D. Decisional consistency, which is, yeah, equation 2. play similar roles at different points within the model. Attentional focus affects how feedback is weighted to the three dimensions in generating a feedback signal. Okay, so that's equation number 4. Okay, over here. So attentional focus is important. Weighs how feedback is given back to right. Okay. While decision consistency D affects how the attention vector weighs. So D is the attention vector. Okay, as per equation number 4. Equation number 4. Right, let me double check equation number 4. So ATT AT. What decision consistency? Okay. Consistent with the last point, Bishara found that fixing either F or D at one and the other to very freely did not result in a statistically significant decrease in the model's ability to fit their participants' data. Okay. I guess for today we'll leave it there. Inshallah, we'll be back tomorrow with another stream looking at the novel dataset being implemented in this model. So it's certainly an interesting equation that's been devised, trying to look at attentional focus and of course feedback signals and understanding consistency in decisions made. So that's interesting. Definitely interesting. Right, okay. So, okay, right. Yeah, I mean, this is quite dense mathematics, but yeah, inshallah, we'll definitely look at this. Till then, Assalamu